I'm the matchless Mr. Daycock, and today I'm going to be teaching you how to integrate functions using partial fractions. So when will this come up? Well, it's come up when you have a function like this that we're trying to integrate, but our denominator can be factorized, and that allows us to write it as partial fractions. Also, there's no other easy way to integrate a function looking like this. Go, what's going on? Can I use the inverse chain rule? No. Can I use some given form? No. So we're going to use partial fractions. So the first thing to do is to go straight to the partial fractions. You kind of just ignore the integral bit to start with. I'm just going to do partial fractions over here, and we're going to say, well, we've got 1 over x squared plus x. Well, that's the same as, let's factorize it, 1 over x, x plus 1. And then for our partial fraction form, a over x plus b over x plus 1. Okay, now, for partial fractions, we need to consider each and every bit. So let's write this out with a little bit of colour. So we've got 1 over x, x plus 1. And we're saying that we want that to be equal to, or equivalent to, no less, a over x plus b over x plus 1. Now, to work out these values of a and b, we have to multiply up till we can get a common denominator between these two. Obviously, we know that the common denominator is going to be x, x plus 1, and so we're going to write that like that, and we're going to end up with 1 over x, x plus 1 is equivalent to a over x, x plus 1. Remembering, of course, we multiplied both top and bottom of this fraction, plus b over x, x plus 1, and then we multiply that here by x. And now from there we can combine this, so we're going to get 1 over x, x plus 1, a x plus 1 plus bx all over x, x plus 1. And now we remember what this sign means, and that sign means that it has to be true for all values of x, which means I can just multiply both sides by x, x plus 1, and I'm left with a very nice simple equation of 1 is equivalent to a lots of x plus 1 plus bx. And again, this has to be true for all values of x. Therefore, what I can do is just pick a value of x, because it has to be true for all of them. So let's pick a nice easy one. Let's pick x equals 0. And why is that easy? Well, it's easy because it's going to make this term disappear. That's the key thing. We want as many terms to disappear as possible, and I'm going to get 1 equals, it's not equivalent now because we've picked a value of x, a lots of 0 plus 1 plus b times 0. That is obviously 0, and we're left with 1 equals a, and therefore we've got our value of a. Similarly, I'm going to pick a value of x equals negative 1. And I'm picking x equals negative 1 because it makes this term 0. And so in exactly the same way, I'm going to get 1 equals a, 1 equals a, lots of negative 1, one colour there, negative 1 plus 1 plus b lots of negative 1. B times by negative 1. So we're going to end up with 1 equals, this goes to 0, plus negative b. Or I get negative b equals 1, and so b equals negative 1. And this gives me the key things I want. I have a equals 1, and b equals negative 1. So now I can use that, plug it in, and I get that 1 over x squared plus x is exactly the same as 1 over x, because a was 1, minus 1 over x plus 1, because b was minus 1. And now all I'm doing is integrating 1 over x minus 1 over x plus 1 dx, because what I'm going to do is I'm going to take this equivalence here and just plug it into my integral. And now that's pretty easy, because integrating this, the integral of 1 over x is the natural log of the modulus of x, the absolute value of x, minus, and this here is just a shift of the 1 over x, so it's going to integrate in exactly the same way. So it literally just becomes the natural log of x plus 1, and then of course plus c on the end. And you can leave the answer as that, but actually what's quite nice to do is remember our log laws and write this as the natural log of the modulus of x over x plus 1 plus c. And that's just using our log laws. And there you go. That's your answer to the first one. Let's go on to the second problem. Here, exactly the same thing. We're going to use partial fractions, and it's just a little bit more complicated. So first of all, partial fractions. We're going to write this as 4x plus 9 over 5x plus 3, 2x minus 1 is equivalent to a over 5x plus 3 plus b over 2x minus 1, which then is going to give us 4x plus 9 is going to be over 5x plus 3, 2x minus 1 is the same as our denominator is, we're aiming for the same denominator, so let's write that in there. Which means we had to multiply the a by 2x minus 1. So we're going to end up with a times by 2x minus 1. And we had to multiply the b by 5x plus 3. And now, exactly as before, that tells us that we've got 4x plus 9 is just the same as a lots of 2x minus 1 plus b lots of 5x plus 3. Now, if we want to make the a term 0, we need to pick x equals 1/2. Now, this isn't required. You can pick easier numbers, so you could pick 0 and 1 and then solve simultaneous equations afterwards. Some people find that easier, but I'm going to go with plugging in a value that makes it 0. So we're going to get 4 times by 1/2 plus 9. You can also equate coefficients. That's another way of solving partial fractions. Is equal to, now the whole point of picking a half was this became 0, so we get 0 there. And we get plus b lots of, I'm going to be in red, b lots of 5 times by 1/2 plus 3. Now, working that out, remembering that's a 9, we get 4 times a half is 2, plus 9 is 11. And over here, we're going to get b multiplied by 5 times a half is 5 halves, 3 is 6 halves, so we get 11 halves. So we get 11 is equal to 11 halves of b. Solving that, we get b equals 2. Now, similarly, what we're going to have to do is pick a value that makes the b term 0. A little harder spot, but it's going to be negative 3/5. So we're going to put x equals negative 3/5 in. This is going to be a little bit more awkward, but still entirely doable. And we're going to get 4 lots of negative 3/5 plus 9 is the same as a lots of 2 times by negative 3/5 minus 1 plus, and the whole point of picking that was we get 0 here. So that term disappears. So here we're going to get negative 12 over 5 plus, let's write this as over 5, so we're going to end up with 45 over 5 is the same as a lots of 2 multiplied by negative 3/5 is negative 6/5, and we can write that as minus 5 over 5. Simplifying this, we get 33 over 5 is equal to, I've been using an equal sign here, an equivalent sign here, that is just equals, and up here as well. I hope people noticed that was inappropriate. So we get 33 over 5a is equal to a multiplied by negative 11 over 5. And that gives us that a must be equal to negative 3. And so now we've done our partial fractions. So we get b equals 2, a equals negative 3. And so we can write down that this is equivalent to negative 3 over 5x plus 3 plus 2 over 2x minus 1. And we can plug that in to our integral. And so we're doing the integral between 1 and 2 of, and we're plugging that in now, 2 over 2x minus 1, rearranging the order to make it a little bit nicer, minus 3 over 5x plus 3 dx. Now we need to integrate both of these, and let's deal with them individually. Let's say I'm looking at the integral of 2 over 2x minus 1. What is going to happen to each of these bits? Well, what's quite nice is, first of all, I could write this as 2 multiplied by 1 over 2x minus 1. And so that gives me a nice bit of leeway. I know that that 2 in front, that blue 2, is just going to come out as a multiple. And then, if I have a multiple on the x, then that comes out as a division when we integrate. So we've got a multiple on the x, so it's going to be divided by 2. And then we're going to deal with just the natural log, and everything inside is going to stay the same. This is our denominator. We're dealing with effectively just the equivalent of 1 over x, but with it turned into a linear function. So we're going to get 2x minus 1. And that will be the integral of that. Equally, in exactly the same way, the integral of negative 3 over 5x, that should be in black, 5x minus 3 dx is going to give us a very, very similar thing. It's going to go like in exactly the same way. We're going to end up with minus 3 over 5 multiplied by the natural log of 5x minus 3. And that gives us our final answer for this integral. We are dealing with the natural log of 2x minus 1 minus 3/5 of the natural log of 5x minus 3, and of course plus c. Everything's got a little bit smushed together there, and let's make that clear with a nice little line indicating where that was and separating it from the rest of it. Okay, and now remembering our integration actually had limits, but also remembering our log laws, we can write this as the integral of the natural log of 2x minus 1, because when we subtract we're multiplying, and then multiples in front go in as a power over 5x minus 3 to the power of 3/5. And we want to evaluate all of that between 1 and 2. Okay, and so what do we end up with? Well, let's plug this in. We get the natural log of 4 minus 1 over 10 minus 3 all to the power of 3/5 minus the natural log of 1 over 2 to the power of 3/5. And we're going to write this as an exact value. So what do we get? We get the natural log of 3 over 7 to the 3/5 minus the natural log of 1 over 2 to the 3/5. And there you have it. Thank you very much for watching, and I'll see you in the next video.